You guys ready for a little geometry lesson? Something different than algebra. All right. So and I'll show you how this relates to the algebra we've been doing with proportions. Similar figures. They have the same shape, but not necessarily the same size. They have the same size, we call them congruent in geometry. If they're exactly the same size, we call them congruent. But similar would mean they have the same shape, but not necessarily the same size. If they do have the same size, we say they are in a 1-to-1 scale factor if they're the same size. Similar figures have the same shape. So what we're looking for with similar figures is that all the angles are the same, right? But it's been blown up or shrunken down so that the side lengths are just proportional with some scale factor. It might be 1-to-4, 1-to-2, or 4-to-1, or 2-to-1. Scale drawing is a drawing that is similar to an actual object or place. Have you guys done any similar scale drawings? You guys done any scale drawings? Anybody in architecture or engineering? You drew a dog, a scale model of a dog?
Yep.
What was the scale when you drew it? It was how many times smaller than the real dog? Really good. Have you guys ever done a scale drawing of your house or a room in your house? Have you ever done that as a project? Have you done that before?
Yeah, I did it like, when do we do those projects where we were like landscapers and
Okay, so you've done it before. Yeah. Landscapers do that. They'll do a scale drawing of what the layout would be for landscaping a yard, right? They worry more about that. A lot of times they'll do that down the hill, when they have full neighborhoods with these fixed little. Whereas here we have the forest as our background, right? You don't necessarily landscape much, but sometimes you landscape a portion of your yard to a certain point. Especially with fire danger, you might want to landscape something not so flammable as cedars and pines and oaks and dry grass. So yeah, that's a perfect example. I've seen it done before where landscapers have done scale drawings of what they're going to do in reality. Have you guys done model airplanes or cars or anything? Those are scale models. If you look at it, they'll have the scale of how many times smaller this is than the actual one. Scale. Here's what a scale is, maybe. It's the ratio of any length on the drawing to the actual length. So here's how it connects to what we've been talking about. Remember, when you set two ratios equal to each other, we have a proportion. So the scale is the ratio of any length on the drawing to the actual length. Write that down. I'm going to be asking you for the scale on some of these shapes. And then finally, scale model is a three-dimensional model that is similar to a 3D object. The three-dimensional model that is similar to a 3D object. Similar means it has the same shape, but not necessarily the same size. It's nice to have a scale model of what you're going to do in reality before you go and do it. And then there are two symbols you need to be aware of. These are symbols that you'll use a lot in geometry. You may have seen them before, you probably have. But this little squiggly thing here is called is similar to. That's what that means. You need to know that. That means is similar to. And then this other one here is is congruent to. Are exactly the same. So it is similar to, and then the other symbols is congruent to. So on this first one here, I'm going to do a little more than what it's asking for here, because on the first problem on both your classwork and homework, they just ask you, rather than jumping right into finding the missing side length using algebra and proportions, they ask you to do a little bit of geometry. And they ask you a little bit about what are corresponding angles and what are corresponding sides. So in two shapes that are similar, the angles will be congruent, so we use the congruent symbol. And the sides will be similar, so we use the similar symbol. Now, when they name these two shapes in geometry, when they name this one triangle ABC, and they tell us it's similar to triangle DEF, they are putting the letters in order to correspond to the letters in this similar shape. So when they say ABC is similar to DEF, they're telling me that A and D, the first letter in each little naming scheme here, are congruent. So when you're asked to do that, we can say that, and go ahead and do this now please with me. A is congruent to D. I know that B is congruent to E, and I know that C is congruent to F. So when they ask you, what are the corresponding angles, this is what you'll write down. Okay, these are corresponding angles. And they are all congruent. And what are the similar sides? Well, we've got AB, and we put a little line over the top. That means segment AB is similar to, using this symbol, segment DE. What would BC be similar to in the second triangle? EF, it goes with the F. Yeah, those are the second and third letters in the naming scheme. And then what would AC be similar to?
D or DF.
DF, yeah. And these are the similar corresponding sides. And so they're going to ask you to do that both in the homework and classwork as the first problem, before they ask you to set up and solve a proportion. Okay. Now, in geometry, it's pretty common not to necessarily label the missing sides as X, but just to think of the missing side here as side length AC. Okay, we would call this side length AC, and we would call this side length DE. So it says, what is side length DE? That's what it's asking for here. Now, if these are similar triangles, I can set up a proportion. It would look like this. 10 is to 16 in the large triangle, as DE is to 12 in the smaller triangle. Notice that this left-hand side, AB, corresponds to the missing side, DE. And this side over here, the 16, corresponds to the 12. Notice how they are written straight across from each other. Now, are there other ways we could set up this proportion and still get the same answer? Yes, there are. We could, what's that? Sure. I mean, we could switch these around, both of them, right? Would be one. But there are other ways we could set up. This is the way I chose to set it up. We cross multiply. 12 times 10 is 120 equals 16 times DE. And to solve for DE, don't let this confuse you here. DE is really representing like X width, okay? But in geometry, that's how we write it. We just write DE, so we know exactly which side we're talking about. And I think that's helpful because I have another missing side over here, AC. And if I call this X, what do I call this? I could call it Y, but you know, we don't need to introduce the letters in there. We'll just call it as it's labeled in the figure. Divide by 16, divide by 16. What do you get for DE then? What is it? Well, we're dividing now. So divide it. 120 divided by 16. What do you get? 7.5. And then does that make sense for this picture, that this could be 7.5 if that were 10? Yeah, it's smaller. So ask that question after you do these. Okay, does it make sense? Because if you mess up on the setup, you might get an answer that doesn't make sense. Like if I got 17.5 for this, either I'm deceiving you with the picture, or you messed up on the setup, okay? Or algebra. Using the same diagram, can we find AC? What would the setup be for AC? What's one possible setup for AC? Let's do this together here. AC over what? 18. You could do that. You could do AC over 18. So this is one possible setup of many. So that's the longest side here over the longest side of the small triangle. Equals what over what? Now I got to make sure I have two numbers involved in this next one. That's what I would, you could do AB and DE. That would be fine. You would have 10 over the 7.5 that I just found. Here's one danger in that. What if this was a multi-step problem and you messed up on finding DE? You know, what if that, I mean, probably wouldn't happen for you guys, but for me, what if I messed up on this? I typed in wrong or something, you know, I just didn't notice. It sounded okay, but what's another option here that would use what's given in the problems? 16 over 12, and that's probably what I would do. I would probably set it up AC over 18 equals 16 over 12, just in case I messed up on the one that I found. Okay, but you know, either one would work. Lots of different setups here. We cross multiply and solve. So we get 12 AC equals 16 times 18 is 288. Then we divide by 12. And AC does, in fact, equal 24. So AC equals 24. And then you got to look at this. Does 24 make sense for this one?
Yes.
Yeah, it's got to be bigger than 18. So 24 makes sense. That's it. So that's labeling the sides of similar triangles and then using algebra to find the missing side length. Tons of applications in real life to this. I'm going to show you several right now. All the rest of them are all word problems. They're all real life sorts of problems. One of them, it would be really fun if we could do it in real life. I'll show you. That's the last problem. You're like, oh, that'd be really cool. That would make El Dorado the best. Even better than what it is. We're already the best, but maybe even better. I'll show you that one in a little bit here. Maybe one of you can design this for us. All right, so here's one. Applying similarity. A sun's rays strike the building and a girl at the same angle, forming two triangles shown. How tall is the building? You know, they were doing this way back in Greek times, right at the, you know, just even in BC. So this is before the turn of the age there, the AD. So the Greeks had this figured out. They figured out that you could get an estimate for the height of different objects by looking at shadows and similarity. It works like this. If the girl here has a height of 5 feet and a shadow length of 3, it goes height over shadow length. It's height over shadow length is 5 to 3. Then I can set it up this way. If I want to know the height of the building, which is X, that'll go on the top over the building's shadow length, 15. So you might want to jot down here, it's height over shadow length, so that we get height over shadow length of the girl and height over shadow length of the building in the right place. And you can use this to get a pretty good estimate. See, I can figure out the height of the girl. It's not hard. I can figure out the shadow length of the girl. I can figure out the shadow length of the building. Scaling the building to figure out the height of it is a little harder. And I'm sure some of you guys could probably do it, but that'd be hard for me. Spider-Man could do it. Climb up the wall and drop down a tape measure or string and then measure it, right? But here it is. We can get the height of that. 15 times 5 is 75 equals 3x. Divided by 3, x equals 25 feet. So one application. See if you can set up the next one. Why don't you try the next one on your own? Set that up, see if you... Alright, we're on a Monday schedule here, so I'm going to show you the setup here. 6 is to 3.5 as x is to 17.5. That's the setup, just to make sure you got that set up, and then x equals 30 feet here. So hopefully you got 30 feet when you set that up. And let's go on. And here's another application of it here. It says interpreting scale drawings. It didn't show up very well on your packet, but I'll tell you what the length is here. It says, what is the actual distance from Jacksonville to Orlando? What you'll see on the bottom left here, you can't see it on yours very well. I know I did it. But it's 1 inch is to 110 miles. So that's what I start with. We've got inches over miles. I'm just going to write that there. And I've got 1 over 110 equals... I'm looking at my map over here. I've measured the straight line distance from Jacksonville to Orlando. It looks like it's 1.5 inches, so I'm going to place 1.5 on the top over x. And of course, this is straight line distance if you're a bird flying there. Of course, the highway doesn't go that way, but this is an estimate of the straight line distance between the two cities. Cross multiply, x times 1 is x. 110 times 1.5 is 165 miles. 165 miles. Why don't you see if you can do the setup for the next one? Set up real quick. It takes just 1 minute to do that. Set up and solve. Alright, so the setup for this one should have been, as soon as I see the scale here, right here, I just grab that and write 1 is to 50. As something is to something, I notice the 6 is in inches. Inches has to be on top, so there's my setup. That's how I think about it. Yeah. If you set it up backwards, 50 is to 1.
No, like, does it matter if you like over x, 1 over 5?
No, that does matter. So it has to be 6 over x because I have inches on the top and I have feet on the bottom, straight across. If I switch it up and do 50 over 1 equals x over 6, that's okay.
No, so like,
6 over x. Oh, I see the 6 over x first. That'll work. Yep, either one of these will work. You should get x equals 300 feet. Yeah. And once again, make sure it makes sense. 1 inch is 50 feet, so 6 inches. You might have just done 6 times 50 and be done with it. All right. So this will be fun. So the top of the E building, right up over here. We can go from the top of the E building down to the flag over there by the track. We have a zip line there. So it says we're going to connect a zip line from the top of the E building down to the flagpole. Using the information on the map to the right, determine how many feet of cable we need. So here's our scale. You got to find it out here. Our scale is 1 inch to 21 feet. So we have inches over feet, and the scale is 1 is to 21 as this is 25 inches on the scale model. That's what we measured out to be, 25 inches per 10. 25 over x. And so we go ahead and solve. How long would that zip line be? Would be a pretty good zip. 525 feet is right, yeah. Cross multiply, you get x equals 525 feet. Have any of you been to the zip line in, there's one over west of here. What is it, I think it's Redwood something camp. I think they have one that might be 1,000 feet long. I just want to say it. Anyways, 525 is a pretty good zip, but they're much longer zips. There's one in Kauai too. I'm not sure if I'll link to that. But, so nobody's been zip lining around here? Have you been? Do you remember what the longest zip? I don't remember either, and I went to the ones. It's over near Occidental. Did you do that one? Redwood. Is that a Redwood?
What's it like yesterday?
Oh, did you?
Yeah, it's awful. But that.
Okay, at Heavenly. Yeah, you don't know how long that one is. Okay, yeah, I've seen that one too. Yeah.